In the triad of thermodynamics consisting of heat energy, Q, entropy, S, and temperature, T, each variable plays a crucial role in understanding the behavior of physical systems. By examining each variable in detail, we can appreciate how they collectively shape the dynamics of thermodynamic processes. Heat energy is a form of energy transfer between systems or objects with different temperatures, moving from the hotter to the cooler object until thermal equilibrium is reached. It can be introduced into a system through various means, such as radiation, conduction, or convection, and is fundamental in changing the state or phase of substances, for example, melting ice or boiling water. Heat energy is the catalyst in our narrative. It initiates the transformation of the system by providing the energy necessary for molecular motion and phase changes. In the context of our pot of water, introducing heat energy causes the water molecules to move more vigorously, leading to changes in the system's other properties, entropy and temperature. Entropy is a measure of disorder or randomness in a system. It's a concept that captures the number of ways a system can be arranged while still producing the same macroscopic state. The second law of thermodynamics states that in any natural process, the total entropy of a system and its surroundings tends to increase over time, moving towards a state of maximum disorder. In the journey from calm water to boiling chaos, entropy increases as heat energy is added. This rise in entropy reflects the increased disorder and number of possible molecular arrangements within the pot of water. Entropy serves as a bridge in our triad, linking the addition of heat energy to the observable increase in temperature, as it quantifies the degree of disorder facilitated by the energy absorbed by the system. Temperature is a measure of the average kinetic energy of the particles in a substance. It is an indicator of how vigorously the particles are moving and, by extension, the amount of thermal energy present. As the entropy of the system increases with the addition of heat, so does the temperature, reflecting the increased intensity of molecular motion. Temperature can be seen as the observable manifestation of the underlying kinetic energy and disorder in the system. It is the outcome variable in our triad, the direct consequence of the processes described by the relationships between heat energy and entropy. In the exploration of the triad of thermodynamics, heat energy, Q, entropy, S, and temperature, T, through the lens of logical triads, we venture into a realm where the principles of physics and logic converge to illustrate the dynamics of physical systems. This analysis seeks to align the properties and behaviors of Q, S, and T with the nuanced frameworks of logical triads, presenting a comprehensive understanding of their roles and interactions in the grand tapestry of thermodynamics. In the state of coexistence, 1a, the mutual dependence of Q, S, and T is paramount. Heat energy, Q, introduces the capacity for change within a system. Entropy, S, quantifies the degree of disorder or randomness ensuing from this change. And temperature, T, emerges as the observable manifestation of the system's collective molecular motion. This relationship epitomizes the essence of equilibrium, 1n, where the absence of net heat flow signifies a state of thermal equilibrium, characterized by a constant not S and not T across the system. The balanced exchange in this scenario demonstrates how each component, in presence or absence, contributes to the stability of a thermodynamic system, mirroring the equilibrium sought in logical structures. The triad further evolves under reinforcement 2a, where the directional flow of heat energy leads to an increase in entropy, culminating in a rise in temperature, thus completing a cycle of progressive transformation. This cycle is mirrored in feedback 2n, where the reduction of temperature diminishes heat energy, leading to a decrease in entropy, which in turn influences the system's ability to further reduce its temperature, establishing a feedback loop that stabilizes the system's state. In examining causal 3a dynamics, heat energy, on Q, directly influences the increase in entropy, S, which then leads to an increase in temperature, T. But an absence of heat energy directly leads to a decrease in temperature, bypassing entropy's direct influence. This nuanced pathway underscores entropy's role as a bridge in thermodynamic transformations. Conversely, reversion, 3n, presents a scenario where the decrease in entropy precipitates a fall in heat energy with an increase in temperature, T, anomalously leading to an increase in entropy, S, illustrating how shifts in conventional roles can reverse the flow of influence within the system. The triad under nonlinear, 4a conditions, reveals an intricate interplay where heat energy, Q, jumps to directly influence temperature, T, which then impacts entropy, S, with the absence of heat energy leading back to a decrease in entropy. This represents a departure from linear causality, embracing the complexity of thermodynamic processes. Retrospective, 4N, analysis allows for a backward understanding of how decreases in entropy can lead to insights about the absence of heat energy and the interdependent relationships within the system. Integrating the triad of thermodynamics within the structure of logical triads not only enriches our understanding of each variable's role, but also illuminates the intricate dance of energy, disorder, and measurable change within physical systems. This synthesis of logic and physics offers a profound insight into the nature of the universe, where the principles of coexistence, reinforcement, causality, and nonlinearity guide the behavior of systems both simple and complex. It's a narrative that unfolds at the intersection of order and chaos, highlighting the beauty and balance inherent in the laws that govern our physical reality. Through this analytical journey, we're reminded of the power of logical structures in dissecting and understanding the dynamic world around us, fostering a deeper appreciation for the elegance that lies in the confluence of theory and application.